So I wanted to show the board working. So here's my kind of temporary setup. What's funny is I actually have my pre-setup. This is where I first started when I was just using an Uno to drive my gates. I had done this in the past using a Mega, but this is a newer Uno with the Wi-Fi. So I was motivated to basically start using Arduino again and get coding. But then, and this also has the time of flight sensors, where before I was using the ultrasonic sensors. But so when I was building this, basically if you look under here, this huge mess of wires, and then there's a breadboard under there. I was like, there's gotta be a better way to do this that's not so messy. And then that's where the custom PCB basically started. And so I first thought it would be way too complicated to do a custom PCB, but it's actually super simple. So over here, really quick, here's my temporary setup. I basically have, it's mimicking the crossing gates. So we have a speaker, we have a servo, we have two LEDs, and then we have a time of flight sensor on the right, and then that's mirrored on the left. And then what we're gonna do is say we have a train coming from the left, or eastbound or westbound. Basically, I'm covering up that time of flight sensor. Time of flight, super accurate, down to millimeters. And then basically the gates are down or activated. And then if the train then goes over on the right side, covers up this sensor, and then this down stop because of the loop, not because of the, and then if I uncover it, you can see then the gates start going up, and then the lights stop. The lights actually don't stop until the gates go up, kind of mimicking the prototypical or prototype. So gates are still going up and the lights are still flashing, and then once the gates are up, the lights stop flashing. So yeah, and then the way that the logic works is when the train passes over one time of flight sensor, it's basically activated. And then on the other time of flight sensor, until it's uncovered, the activation won't stop. So that basically accounts for the whole train, and then the end of the train will basically uncover it and then stop the gates. So I'm gonna go ahead and unplug this so it's not going off when I'm trying to explain some other things. So just wanted to show really quick the kind of progression of the boards. So this was the V1 PCB board. I ordered 5 of these, minimal quantity from JLCPCB. And yeah, so you can see it's pretty big. It's got a lot of stuff going on it. And when I talk about the easyEDA side of things, I'll explain more about what's actually on here. So this was V1. And then here's V1 after I first got it, and I soldered my own components on there, and you can see pretty quickly I messed up. I had some orientations wrong. I had to solder on some wires on there to bypass some things, but again, this was the first time I made a board, so I learned a lot. And you can see I had the LEDs in there, the resistors and everything. So yeah, this is V1. And then V2 basically, so after I had V1, I learned everything I needed to learn. Or not everything I need to learn, but I learned a lot more than I knew originally. I did this V2. This is a PCB-A. The A basically is assembled. And so it basically means at the factory, they basically add a ton of, they add the components to it for you. And so the reason I didn't do that the first time is because I thought it was super expensive. I didn't know about the BOM file or the placement file, but then after doing some research, it wasn't that complicated. And I didn't do everything, so you can see the female headers for the Adafruit and the Nano aren't there, and then the potentiometer on the top right. The reason I didn't do those, I think the potentiometer, I couldn't find the right one at JLCPCB. I was looking for a specific one, and they just didn't have it, and then I was able to solder that on myself. And then for the female headers, I think I was deciding how I was going to actually attach the boards to this, whether I wanted to use headers or not, female headers or not, what's like shallow headers, so I just didn't do it. So this is how it came from the factory. Yeah, so you can see basically I have a fuse in there, I have a bunch of LEDs, resistors, capacitors, the DC power intake, some voltage regulator. So this basically is 8.5 volts coming in, and this will drop it down to, I think it's dropping it down to 6 volts. It's been a while since I've been in the EDA side of things, but once I get back in there, I'll refresh my memory. Now the Nano needs 5 volts, but it's fine taking the 8.5 and dropping that down to 5 itself with its voltage regulators that it has built into the board. This voltage regulator is for my servos. So the power basically comes in here. One shot goes straight to the Nanos, and then one goes to the voltage regulator, and then this voltage regulator goes specifically to the servos. to kind of separate that. In V1, I actually had 2 DC inputs and a switch. Where's that other board? I had this switch on here. And it was basically, did I want the servos to be powered by this? So the board and basically the servos were powered by one DC input, and then the switch basically allowed me to have the servos powered by their own DC input. And then I went away from that in V2 because I wanted to simplify things. And then I have some LEDs mounted on this board as well. Some text about the configuration. In the top right, I have this little E+E for my daughters. It's just a little shiny solder mask, which is kind of cool. And then, yeah, here's the back. This is a 2-layer board with a ground plane on both layers. I have the blue color. They have different colors: black, green, red. But I thought the blue was nice. And then if we go to the actual board here, so you see the things I had to solder on myself was the potentiometer up here, and then the headers for the board. Let's see if this focuses. So you have the Nano right here, the Arduino Nano, and then you have the Adafruit soundboard with the amplifier. So you can see it's driving the speaker. Some of the Adafruits don't have the amplifier, so you'd go up to an amplifier board. This is a built-in one, and then this is an 8.5 DC coming in. Hey all, I wanted to share with you my model train crossing gate, basically custom PCB project. So what we're doing is we're starting an easyEDA. If you're not familiar with easyEDA, there's a ton of YouTube videos out there. That's actually how I learned how to use it. They basically walk you through what it is and how to use it. I'm not going to spend too much time on that for this video because this is more about my project. But if you're looking to do something similar to this, I highly recommend you start there. So easyEDA is basically just an ECAD program. ECAD is basically how you build PCBs and design circuits and all that. And what you're looking at is basically like a blueprint, right? So this is a blueprint for my circuit. If I drag around here, you can see, it even looks like a blueprint as far as has the current revision, the sheet, the who drew it, company, etc., the title. So this is my board, my revision 2 board. And so there's going to be a video either before or after this part that demos the board, but just for a recap, you basically have a microcontroller driving this PCB. So when you're thinking about the PCB, it's really, the one I built is really more akin to like a motherboard or a Arduino shield, and that's in the sense because the microcontroller driving it is not built directly into the PCB. It's a separate board. Eventually, I want to potentially try to make my own PCB that has a microcontroller, or not a microcontroller, but a microprocessor built into it. So I'm not relying on a Nano, but that's probably a little more advanced for me. So in this case, I'm relying on the Nano. And the Nano is a good board because it's super small, has a ton of GPIO or IO pins. It has I2 squared bus. It has the one I have, the Arduino Nano, has 2 hardware serial connections, and then it's just a good board to work with. So I'm starting with my Nano right here, and then you can see all these different things are connections, right? So all these little call them tabs, or little finger looking things, basically map to somewhere else in this schematic, and then that basically just helps you so you're not drawing wires everywhere, or traces in this case, or routes. And so like the status 1 actually goes over here to status 1. So the output of this status 1, which is A0, analog 0, goes into an LED, and then it goes into ground. And then you see everywhere where it says ground or VCC, that's a common voltage or common ground. So you can see the ground coming out here, and then all these are the ground. And then you can see the VIN, which is a 5 volt, or VIN in this case is basically the voltage coming into the Arduino. 5 volt is going to 5 volt here, and VIN is going to VCC. So that's basically the whatever power is coming in, coming out type scenario. And then, so, okay, let's start. So that's microcontroller. I just wanted to explain that piece. But so starting in the top left, so you basically have a barrel jack coming in. For this project, I'm using 8.5 volt DC. and I chose that basically because I need to drive my servos and my Arduino board. With the Arduino board, I think it can take anywhere from 12 volts to 6 volts, 6 volts minimum, and then the 6 volts minimum guarantees that the 5 volt is the 5 volt coming out. Anything less than 6 volts or 5 volts wouldn't be guaranteed. And so I wanted that, and then I'm also then driving the servos, but I'm actually doing something a little different down there. So yeah, so here's the barrel jack coming in. It hits a fuse. I was just told it's good best practice to have a fuse on your board to protect your circuit. The fuse is basically based on the rating, so this will pop at 3 amps basically, and then it goes into the VCC, and then it goes into a capacitor, and then it goes into the ground. The capacitor has voltage on one side, ground on another, and the purpose of that is basically to smooth out that wave. It's because you have dirty power coming in, and then once it hits your board, you want it to be as clean as possible. So you basically have these strategies where you have these capacitors at certain points of the circuit. So it goes from the barrel jack in to the fuse into the capacitor, and then from there it kind of goes into a couple different places. So one place it goes into the VCC on the Arduino. Yes, I'm using it as input, so it goes into the VCC on the input. Again, there's another capacitor there to smooth that out before it hits the Arduino. And then the other place it's going is into a voltage regulator, and it's a step down or drop down, or I think drop down, drop down. I've already forgotten the terminology, but it's basically taking the voltage from 8.5 down to 6. The one I chose, and the reason I'm doing that is because these servos require a max voltage of 6 volts DC, and so obviously they couldn't take the 8.5 because that's too much. And so I'm dropping it down to 6, and then there's some capacitors there. So you actually can see this when it goes into the voltage regulator. It's got that VCC, which is 8.5, and then the output is a 6 volt, and then that 6 volt then maps to here, and here. So you can see basically how the schematic works. This little section right here is basically the capacitor piece, but it ties into then over here, which is into this is a servo. It's like three male headers on the PCB, and then those 3 male headers are pretty typical for a servo. So you have ground, the voltage, and then the signal pin. The signals pin are actually associated with the Arduino Nano. So if I come over here, you can see servo 1, servo 2. So the traces on the PCB are going there. So that's the servos. Over here you have the LEDs. So the LEDs are basically using, so I was running out of GPIO pins, and so these gates that I have a common, they have 4 LEDs on them, left, right, back, front, and then they're using common, the 5 volt or the voltage is common, and then the ground is separated, and then I think separating or setting the ground to low, I think, is what drives these in this particular LED. So the 5 volt coming in here, and then that 5 volt basically is being split from a wiring perspective. Trying to remember how I wired these up, because I know I'm sharing the voltage, or I can't remember. I have to look at the wires, but it was basically because you only see there's 2 outputs here, but I'm driving 4 LEDs, so I know I'm putting 2 LEDs on LED 1 to LED 2, and 2 LEDs on LED 1 and LED 2 over here. Again, just because I ran out of pins, and the voltage splitting and the math came out where it's a red LED, so it requires a little bit more voltage, but it's still bright enough after I split them in it without having to use a pin for each LED. But again, this is similar to the servo. But this is a JSP connector, if I remember correctly, or JSP-XH or something. It's basically those little white connectors that everyone's familiar with. I actually had to buy a kit so that I could connect them. I think you might have saw that in the other video. So yeah, this is a JST connector, and then again 3 wires going out, and then the 2 wires are basically being shared, and then the 5 volts being shared. Over here you have the Adafruit board. So this is a Adafruit board with a built-in amplifier, and then there's a couple different ways to drive this board. Usually I was driving it with a GPIO, which means you basically have pins from your microcontroller going into all these over here on the left. So like 0, 1, 2, 3, 4. 0 correlates to a sound file, and then that sound file, based on how it's named, either loops or plays once or and so forth. So you can drive it in that mode. I'm actually driving it in UART mode or hardware serial mode, because I wanted a little bit more control over it. Plus, I didn't want to sacrifice all my GPIO for my Nano, and so then to drive it with the UART, basically I'm using just 3 pins versus, you know, if I had like 6 sounds, it would be 6 to 7 pins with the with that configuration. So the 3 pins are basically, there's a reset pin. So the reset pin is you know, it's not required for UART. I think this UG pin right here, setting that to ground, I think was sufficient to put it in UART mode. I think I wired up the reset just in case I ever needed to put the board in reset mode. Then the TX and RX are basically going to the second serial on the Nano, and then there's a capacitor again on here, just cleaning out that the voltage 5-volt signal coming in, and then everything else, all these X's mean they're not being used. All the grounds are common grounds, and again I'm setting that UG to ground, basically to put it in UART mode versus GPIO mode. And then over here, sorry, let me zoom back in. Zoom in, come on. You have a couple buttons, a potentiometer. So the potentiometer is going to control 3. I think control 3 is an analog pin, right? Because it's a potentiometer. And then the buttons are going to analog pins as well. And then I'm using them as analog. Some of the analog pins you can use as digital pins, with the exception of, I think, of A7, which is I'm not using because it's analog only. And then some of the other pins are basically digital analog. But yeah, so these buttons are pulling down to 5 volt. Oh, that's a good call out. So pull down or pull up, right? Pulling voltage down or pulling it up or so forth. So right here there's a resistor in the schematic, basically to make sure the button gets pulled down properly, so then it, you know, registers cleanly as on or off. So you can read all about like pull up resistors and pull down resistors, and based on your schematic you'll use one or the other. Because over here I'm using pull up resistors for the I2 squared bus. I think I'm pulling it down, or I think it was the inverse, pulling down the buttons and maybe up the I2C bus. I don't know, I remember I just did a ton of research on the best way to set things up, and they recommended having the pull up or pull down on the I2C squared. Pins 1K to be tested. I remember I had notes. Oh, pull-ups. Yeah, so I had pull-ups here and pull-downs. Yeah, so again, I had these notes, and then with a 1K resistor. Yeah, 1K. And that was just the recommended for the I2 square bus. Over here, I have the extension port, which basically, because of the I2 squared. So, or let me talk about the time of flight sensors really quick as I'm moving my way down. I think I skipped over those. So right here, basically my time of flight sensors. So the time of flight sensors that I'm using are driven by I2C squared, or the I2C squared protocol, which is basically a protocol supported by a lot of microcontrollers, and it allows you to do more of like digital communication with sensors. It actually works really, really well. And so what's going on is so on my Arduino board, again, you have the SEL SDA pin, which is for the I2 squared protocol. And then each of my time of flight sensors gets those inputs. And then each time of flight sensor also gets a 5 volt and ground. And then each time of flight sensor gets a GPIO pin. And the reason they have a GPIO pin is because the time of flight sensors that I have, they don't allow you to change the address on the time of flight sensors with anything on the board itself. So like a little jumper or some sort of switch, because they're super small. So you have to do it via software, and you have to do it basically every time the microcontroller boots up. And so the GPIO pin basically puts the time of flight sensor into a reset mode. And when it's in that reset mode, that's when you can change the address. So basically when it's booting up the program, it's going through each time of flight sensor one by one, putting it in reset mode, setting the address, then going to the next, and so forth. So the board basically supports 6 time of flight sensors. In the demo, I'm only using 2, but I'd say if you had like a 3-track main line, you could, in theory, have 3 sensors on one side and 3 sensors on the other side. And then over here to the expansion port, this is also driven by the I2 squared bus, has its own 5-volt and ground, and then also has a GPIO pin just in case. And then the genesis here is basically, if they ever wanted to add additional functionality in the future, they build these IO expanders, GPIO expanders, that are driven by I2C squared. So I could, in theory, add more GPIO pins via a expander, and that would use the I2C squared. And then over here you just have some LEDs that are built into the board. And then the buttons, like I was saying, you have the potentiometer and then the 2 buttons. So that's pretty much it for the schematic side of things. So this is what you build first. This is how you define your circuit. Oh, you know what? I skipped over here. The mounting holes are grounded. Again, just best practice that I was told. So yeah, so you're kind of building the schematic here in this kind of blueprint, ECAD visual. And then once you've kind of built this out and feel good about it, you then basically can come up here, go to design, convert to schematic to PCB, and then that basically builds something like this. Now it doesn't look exactly like this because this actually has the traces and everything routed, because this is the version that got sent to JLCPCB. But what it would look like if, let's see if I can do a fresh one. So convert this. This is basically setting up this magenta line as your board footprint or board, and then you see how it just kind of throws everything on here. The blue lines are the connections that I established in my ECAD, and then you basically just start placing things on your board where you want them to make it look nice and neat. And then once you have all your components kind of where you want them, then you actually start connecting them via traces and vias and so forth. You can do it manually, or you can use auto route. Auto route will do its best bet to kind of connect everything. It does a pretty good job, but then any professional will tell you not to use it, just because of like signal to noise and trace thickness and distance between traces. I mean, yeah, there are some parameters you can set up in auto route to set a minimum trace distance between traces, or to make traces thicker based on the type. So like if your voltage trace needs to be thicker than like a ground trace or just a signal trace, you can do that. But again, all those intro videos to easyEDA, we'll talk about that. So let me close out of this. So here's my schematic, kind of assembled, traced, everything's routed. You can see that I have ground planes on this. This is a 2-layer PCB that I did. I have everything kind of, and all these are basically the silkscreen layer. So I have all the text, the logo, everything on there. And then I have a solder mask layer that doesn't look like it's showing. Let's show this in 3D. So let's go to 3D. So this is the 3D visualization of this. And then I must not have it on this. Oh, this is R2. Oh, hold on. Let me skip over to, so I basically just went through. Let me go to this PCB. So that was R1. That was my PCB for R1, which is why it looked a little weird. Here's my PCB for R2. So ignore the R1. Here's R2, and you can see R2 is much different. I'll actually open them up so you can see them. See, R1 has square corners. It's much bigger. The tracing is not. I actually use auto routing for R1, so you can see some of these minimum distances and everything, and some of the way that they're going. So this is R1. R2 was not auto routed. It was manually routed, and you can see there's definitely more distance and thicker traces for power, and things are just a little bit more neater. And then I have the rounded corners up here, which is just a little bit nicer. And then I still have 2 ground planes. So let me go to 3D view here. Yeah, this looks much better. So you can see here there's a ground plane on layer on the bottom layer, and the ground plane on layer 2. This is the 3D view. So in here you basically can do a couple different things. So I can turn off those 3D models. I can say, I'm gonna tell JLCPCB I want a black board, and I'm gonna have silver traces because it's cheaper. Go back to gold. So this is how you can visualize that, and then I can then say, give me the 3D models. So this even helps you further how to visualize how it's gonna look. So you can see the 3D models. There wasn't a 3D model for the Adafruit board. I think I made that footprint myself. Just because there was no good existing footprints in the library, so there was no 3D model associated with it. But yeah, this is the 3D view. So you can see for the servos, that was the three male pin headers I was talking about. All the white things are the JST headers. This one's driving the lights, so you can see the 3 pins. This drives all this time of flight sensors. It's basically one big JST sensor. I think it's a 15 pin, 3 times 5, right? It's 15. And then you can see over here the nano, the place for the soundboard, and then you can see the DC in barrel jack adapter. You can see the expansion port. You can see the voltage regulator, the fuse. Everything's depicted pretty close. You have the buttons up here, the potentiometer. It's not on here because they didn't have the specific potentiometer that I was looking for. And then the LEDs, and then up here you just have E and E for my kids, which is shiny in the solder, which is kind of a cool touch. And so yeah, here's the board, so you can see it in 3D. You can see it in 2D if you wanted to. So as you guys saw when I printed out. So yeah, this is easyEDA. When you're ready to send this over to JLCP, it's actually pretty simple. So one thing, since this is I'm doing a PCB-A here, assembled, here's my bill of materials. And you see all the parts that are basically assigned here. And then I also have a pick and place file. You need that for a PCB-A. And then to send this over, you need a Gerber file. So this PCB fabrication file, which is a Gerber file, and then one-click order to JLCP. So this, when I'm generating the Gerber file, it's basically going to check all my traces. So I did a quick check there and passed the validations that I set up. And then what you can do is, here's kind of a preview of your final PCB board. Again, you can change the colors. This site doesn't actually show it in the rendering, but basically what this is a quick way to send these over to JLCPCB. So you can either generate the Gerber as a zip file and then send it over to like a PCB way or another manufacturer, or if you do this one click to order a PCB SMD, SMT as surface mount, this will send it over to JLCP with the BOM file, the placement file, and everything. So it makes it super simple. And again, you see the two-layer board. So I'm trying to think if there's anything else I want to show on here. If I go back to the easyEDA file, and then you can go to common library. So when I was dropping everything on here, basically these are all your built-in things, the common library. So you can find capacitors, resistors, and they have different sizes. So these are all the different common sizes of a axial resistor. So that's basically how you this is the footprint, basically definition. Sorry, let me go back. And then as you go down here, you have different ones. So you have some LEDs, or you have diodes and LEDs. You have diodes, which basically control the flow of electricity one direction. Then you have the LED, which is the light emitting version of that. Regulators, and then some more advanced stuff down here with like OLEDs. So if anything is not in this common library, you basically go over to this library, which allows you to sort. So if or allows you to search, and then basically you want to put in the database that you're searching. So if I'm searching, let's see, so say I'm doing a PCB-A, so I really want to work within the JLCPCB assembled. So these are the components that JLCPCB has. It'll tell you if it's a surface mount component, it'll tell you the price of it, and you really want to pick from here. So if I'm looking for an LCD module, you could search here, you could find your LCD. This will show you the footprint of it, so that it shows you all the pins, and then you can drop this into your project, and then you can then safely know that JLCP, and then you can see right here it's trying to drop it in my project, and then you can then safely know that part you could get ordered from JLCP. And then here's the price down here. I don't know why it's showing 0. They must be out of, oh yeah, there's 0 stock. But so like, let's go to this one, which has 14, and then they're $2 and 11 cents per component, which is pretty cheap if you think about it. And that's just a simple LCD. So let's close out of that, and then this is the JLS page, which is associated with JLCPCB. I don't know if they're the same company or they just support each other, but again, this is how you can find components. So say I'm in here and I know I wanted this component, so I could then go back to JLCPCB or go back to easyEDA. I can then go to the library, search for that particular number, find that surface mount part, look at the footprint, look at the actual picture of it. The bottom, this is the footprint right here. The other one is the schematic. The footprint is basically how everything connects. And then I could drop that into my my schematic as well. So yeah, so you can see I can drop that in here. So yeah, that's easyEDA. Again, watch the other video about the circuit board, or the one that shows the circuit actually working. And then yeah, that's it. So I'm not going to show the code for any of this. Hope you enjoyed this video. If you have any questions, please reach out. Thanks. One other thing I wanted to show was basically this binder. So when I was doing all this, I was figuring out how everything worked. And so basically starting with the nano that I had, basically the pinout is important, just to understand what pins are obviously what, but then which ones can do serial, 1, which ones are digital only, which ones are analog only, just because that was important. The SCL, SDA pins, because that's important for the I2² protocol, and I'm actually using that to communicate with the time of flight sensors. And so just having a diagram like this to start with, you know, I can completely understand kind of my pins and my ports, and I basically took that into easyEDA. And then the second one, so you can see this is the V1 board. So here's all the notes that I was taking when testing the V1 board. You can see there's a ton of notes. Here's when I was actually checking if things worked with the check marks, and then just some notes. So like this was V1. This is part of V2. This is I think this is the BOM. Yeah, it talks about the different parts. I'll talk about that more in a second. This is the printed easyEDA file, or ECAD, or whatever you want to call it. So you can see I spent a lot of time making sure this was clean and neat, well documented. This is the final V2 rendering, 3D rendering, or in this case it's 2-dimensional, and it doesn't have any of the parts on there. You can have a part view. I think I have that on there next. So again, just making sure I was accounting for everything, and you see the different symbols for fuse, voltage regulator, capacitors. I have an expansion port, which basically wasn't being used in this demo. So if I go over here, this is an expansion port that is tied into the I2² bus. It has power, it has additional pin in case I ever want to do anything with it. And then here is the 3D version of everything. So you see I was, again, taking notes, making sure I understood where everything was. This one has the parts on there, the rendering. It has a nano in there, it doesn't have a soundboard. So yeah, just making sure, and this is revision 2, version 2, R2V2. And so yeah, just being super neat and making sure, you know, everything was important. And then on the BOM file, so this is basically just, you know, when they do that PCBA, the assembled from the factory, they need to know all the specific pieces, the footprint, and then the part number. And then they use this to basically say, you know, I want this piece in this particular place. So this is the part number of the number of the part, which correlates in their system. And then I think the footprint is probably the most important piece over here, because then the footprint is in the schematic, and how it correlates where that part actually goes. And then there's a placement file too. So yeah.